want you to notice what's on this graph. The first strand goes from lithium to fluorine, and then it stops. And then the next strand goes from sodium to chlorine, and then stops. And then from potassium. Now there are some D elements in there too. Again, we're not ever going to pay attention to any trends with the Ds. Only with the S's and P's really, with the main group elements. There's a general trend every time to go up in electronegativity. This is the exact opposite trend from atomic radius that we just saw. As atoms are getting smaller as we go across a row, the electronegativity is going up. Remember, this has to do with the pull on electrons. So the more the outer electrons can be pulled, well, really, that's due to the fact that they're smaller. The smaller atoms have more of a pull on the outer electrons. JD?
Like in a lab or something, could you ever force a noble gas to bond with another element?
Yeah, there are some compounds with xenon, like xenon tetrafluoride, ZeF4. But yeah, that does not occur naturally. Like if you put xenon and fluorine together and you heat it up or whatever, they don't want to react with it. I don't know exactly what they do with xenon, but there are several compounds of xenon. And recently I've heard that there's some compounds with krypton too. Originally it was thought that xenon could, because it's so much bigger, it can expand its valence shell and use some d orbitals too to bond with. And they've been able to with krypton too. But what they do to make that happen, I don't know. So yeah, down here it says the noble gas, in fact I said most noble gases don't bond because we don't know of any compounds that involve helium, neon, or argon, only starting with krypton. So we don't even give them values of electronegativity because electronegativity is how much atoms are pulling on bonded electrons. Well, if you don't make bonds, then you can't have an electronegativity value. So yeah, it's a clean trend for electronegativity. We don't have any unusual dips in the middle of a row or anything like that. We start low and go higher every time. Again, with these Ds, the Ds are unusual. We don't worry about them. There's so many orbitals in there and so many different things that can happen, we just forget about it. So main group of the black ones, low up to high. In fact, oh, here's an interesting thing. We're not going to worry about that either. Iodine is lower than the one before it. Sounds good to me. Let's go on to the next one. So just to make this clear, I have a slide for across the row and down a family, but really all you have to know about electronegativity, as the atom gets smaller, its electronegativity goes up. So where the biggest atoms are on the bottom left, francium is the big boy. It's big in size, but it would be low in electronegativity. Because those outer electrons are so far away, when it's bonding, it doesn't have any ability to pull the electrons toward itself. Okay? So, across a row, the atom's getting smaller, and therefore it's able to pull on outer electrons more.
Don't if you mix francium and water, doesn't it explode?
Yeah, it would explode. Yeah. Because francium has a low ionization energy, it doesn't mind getting off its outer electron. So yeah, it would oxidize, and then the water would reduce, and it would be
Let's do it.
pretty reactive. I have never seen francium. Francium is super radioactive. It's really expensive. Yeah, I've never dealt with it. I never saw cesium either.
There's a video, I think I've seen cesium. It was pretty bad though.
In water? Cesium in water?
Yeah, they had to shoot the video from like 100 feet away because the first camera they tried it, like when they touched the water, it destroyed the camera.
Ah!
Look it up.
That's fun. Okay, let's go on to the next one. So this is across a row, and then the next one is down a family. Now let's take the most obvious family here, the halogens. I say obvious because they're on the top of every strand. Fluorine, chlorine, bromine, iodine. What's happening to the electronegativity as we're going down the family? It's going down. Yeah, and it's going down because the atom's getting bigger. It's just all the same kind of concept that repeats. Electrons are farther from the nucleus because they're bigger going down, and so the pull on shared electrons is not very high. Those are our two final periodic properties. I told you I had one bonus concept for you, and that's ionic size, when atoms form ions. I know I'm getting that look like, oh, not into it more. Too bad. It's bonus. I thought we liked bonus stuff.
Only when I can get extra credit.
Yep, you can. Alright, Spencer, let's go on.
Sorry, not today.
Ionic size is pretty easy, so even if you're not into it, it's super easy. When an atom loses electrons, there's a couple of things that happen. First, you might lose a whole energy level of electrons. That would make it smaller. But also, you now have fewer electrons than you have protons. That means the atom is proton heavy. Being proton heavy means that the remaining electrons that are still there in the atom get drawn in more tightly. Again, you're proton heavy. That means that you got more protons than electrons. So, when you have lithium losing its electron, it gets much smaller. The size changes a lot when atoms form ions. Sodium gets a lot smaller, potassium gets a lot smaller. All these are losing an electron. When you have an atom gaining an electron, the opposite happens. You start with fluorine, far to the right, as a neutral element is very small. But when it gains an electron, boom, it balloons out like that. Chlorine starts small, but then gets big. See how big these things get relatively compared to when they were neutral. So what you need to remember is an ion that becomes positive is going to get smaller, always. An ion that becomes negative is going to get bigger. Much smaller and bigger, too. It's not just a subtle change, it's a big change.
What's the unit on that? It's like a little egg with a circle over it.
Thanks for asking, too, because I did want to mention this. You'll see this sometimes. That represents an angstrom. Angstrom is a very common unit when we're talking about atomic size. Oops, I spelled it wrong. It's ROM. It's probably named after a person, I'm not sure. And why the symbol, I don't know, they just called it A with a 0 on top, or a degree sign on top. And that represents 10 to the negative 10th meters. So it's like 1/10 of a nanometer. Because a nanometer is 10 to the negative 9th meter, so it would be 1 power of 10 smaller than that. Don't be surprised if you see angstroms on the AP exam too. And don't freak out, you're never going to have to convert with angstroms. I don't think they'd have you do that. It's just for comparing. Okay, but it is a common unit of atomic size.
For the quiz, if we leave in meters as opposed to nanometers. Is that-
Unless it asks for it in nanometers.
Okay.
Only because nanometers are like the common unit of wavelength. The official one, systematically, would be meters. It's fine. You okay with that?
Yeah.
All right, one more slide. You don't have to write anything, you just have to look and guess. In between each pair, which has a bigger radius? Magnesium or magnesium positive 2? Which one is a bigger radius? The neutral magnesium. The Mg plus 2 has lost its 2 valence electrons. Now that's gotten a lot smaller. Losing 2 electrons, it's got 12 protons trying to only hold on to 10 electrons. So those remaining 10 electrons get drawn in very tightly. So yeah, the bigger size is going to be the magnesium. How about between calcium neutral and sodium ion? Remember what happens to sodium, it doesn't just get a little smaller, it gets a lot smaller. So I know that calcium is a little farther to the right, but it is down one. So yeah, between calcium staying neutral and sodium losing an electron, calcium is bigger for sure. For sure. It's a lot bigger than the sodium ion. Now if I asked you calcium versus neutral sodium, that's kind of a toughie, because sodium is a little higher, but it's farther left. But since I had a sodium ion there, that's a giveaway. Sodium ion gets a lot smaller when it's ion. All right, what about chloride ion versus bromide ion? Which one is a bigger radius? Bigger.
Bromide.
Bigger.
Bromide is bigger.
Bromide is farther down. They both have the same charge, so the bromide ion wins. Yeah, it's bigger. Okay, here's the best one: fluoride ion versus oxide ion.
Fluoride.
The same. Or Or no?
They both have 10 electrons.
Oxygen has less protons.
What?
Oxygen has less protons.
There's fewer protons in oxygen, so that doesn't have as much pull as compared to the fluorine, does it? You got 8 protons holding 10 electrons for oxygen. You have 9 protons holding 10 electrons for fluorine. Which one is bigger? Is the oxide, because it cannot hold those 10 electrons as well as the fluorine can. Are you with me on that one?
No.
Yeah.
What percent?
8 protons for oxygen holding 10 electrons. Now, of course, they're in different energy levels. I'm just making it look like that. Now you got 9 protons for fluorine holding the same 10 electrons. Are those 10 electrons going to be able to be pulled in more tightly, or is it going to be bigger? With a bigger charge. The bigger charge on the nucleus is going to hold the electrons in more tightly. Oh gosh, that's not a good representation. I have to make my radius smaller for this one.
Uh-oh.
And that's not very round. But yeah, the more protons you have in the nucleus holding the same number of electrons is going to make for a smaller radius. So this one would be the bigger atom, or bigger ion, the oxide ion. Finally, magnesium ion versus chloride ion.
Well, that's a tricky question.
I don't think it's tricky.
Alright.
The bigger one is going to be the chloride, yeah. Because the magnesium is far on the left, but it becomes a positive 2. It goes way smaller. The chloride ion started as a neutral small because it was far to the right. Boom! It got bigger because it became negative. So which one is bigger? The one that got bigger or the one that got much smaller? Well, it's going to be the chloride ion.
Get big.
So it wasn't a trick question.
No. Typically, when you're comparing the size of a negative to a positive, the negative is going to be much bigger than the positive. Okay? So it's 10 o'clock. Whoops. I'm done. So you have a quiz tomorrow.